Welcome to our weekly seminar. Decided that you could all make it. Yes, we do have Dr. Richards with us. We'd like to invite Jacob Lewis to come say the opening prayer for us to kick it off. Our dear Heavenly Father, we are so very grateful for the opportunity we have to be here today. We're grateful for our speaker, and we ask that we'll be able to listen and learn. And please bless that as we continue towards finals week and the end of the semester, we'll be able to have Thy Spirit with us to complete the things which lie before us. We say these things in the name of Thy Son, Jesus Christ. Amen.
Amen.
All right. By way of announcements, we do have quite a few announcements going on as the semester wraps up. We want to remind you of the STEM program that we have every second and fourth Wednesday to help the local elementary school students have a little STEM activity. So if you're interested in participating in that, talk to Chris Edwards, or there's also lots of information on the blog about that. This evening at 5:30 p.m. there is an ARIMA forum with BNSF, who is coming to speak about railroad engineering and railroad construction. That's today at 5:30. Some of you may know, but we are we're helping security with basketball games. And so we had the opportunity to go and act as a security guard and check people's bags as they come in as volunteer opportunities. So if you still need service points, it's a great opportunity to get those in one foul swoop. I think they are kind of long. It's about a 4-hour, 5-hour shift, but it's kind of cool to be involved with that. So see the blog or Shane for more information regarding basketball security. We do have a Structural Engineers Association of Utah webinar coming up on December 5th at 6 p.m. Those are usually great, and there's usually some food involved with that, so come if you're interested in that. We still have lots of these nice new royal blue polos, so if you're interested in buying one, please do so online, and then contact us as the officers, and we'll get you your shirt. We have a Central Utah branch luncheon today in Pleasant Grove at 12 o'clock. If you're interested in going, I think that they're going to meet out here at around 11:30, so you have to sneak out of seminar quietly and then head up to Pleasant Grove for that. We do have an opportunity to volunteer with the Utah Underwater Robotics Club. Check the blog for more information on that. And the seminar is fast coming to an end, so please don't procrastinate your service points or your leadership points, so please contact us. We have tons of opportunities these last few weeks to get those done. So let us know if you have any questions about any of that. And then, like usual, we have regular concrete canoe, steel bridge, and EERI club meetings. Here's a quick slide about the BNSF information session tonight at 5:30 in 404 of the new engineering building. And lastly, we do have officer elections coming up. So I know if any of you are interested in running to be an ASE officer, it's a great opportunity. I really enjoyed being an officer this past semester. And so we invite you to nominate yourself and nominate any friends you have who might be interested in running as an officer. So please do so online. There's a couple links that have been sent out as well as on the blog to nominate people. So please do so. I know there are a few requirements up there on the top right. You do have to have a GPA of 2.5 and a few other commitments, so please verify you meet those commitments. Next week's seminar, we have a cool opportunity where the National ASCE President is coming to visit us and speak to us in seminar. So it'll be a really neat opportunity. Her name is Christina Swallow, and she'll be speaking to us. So please make sure you're here on time and give her your full attention as we do all our seminar speakers. For those of you who don't usually come, we invite you to come, even if you usually watch it via video to be here for that. So today's speaker is Chris Olson, and he is a graduate of the University of Utah in civil engineering, and he works with Dunn Associates. And so we'll turn the time over to him for our presentation today.
Sound all right? Okay, good. Well, I'm sure by the time this is over, you're all going to be thinking, I can't wait for Christina next week because she's going to be so much more polished and not nearly as nervous as this guy standing up here. So full disclosure, I am fairly nervous. If any one of you came into my office in 2, 3, even a group, and we started talking about some engineering principles or something that needed to be resolved, man, we could do that, and I'd be happy to do that. But standing up in front of a group like this and spilling my guts feels very weird. So I don't know if I like it a whole lot, but it is what it is. So again, if I'm sweaty and nervous, please recognize that this is out of my comfort zone. And I heard finals week, and one of the topics or ideas that was presented, like, what would you want to tell some students that maybe you would have wanted to know, or something like that. So before we talk about whatever's up here, I will just say this, like, I guess in the back of my mind, I would have recognized, oh, it's probably the end of a semester, and there might be close to finals week, but I graduated in '96, and I can't even, it's a weird idea. So I understand for you guys right now, finals are like everything, right? You're like, you got these service points you got to get, you got to do all these papers and all these different things, but there comes a point when you just realize, oh my word, I guess the semester started, did school start, and now school's over, and it just happens. So for whatever, take that for what it's worth. If you're right now like feeling drowning and overwhelming and like, you're overwhelmed, like, oh, I got an overnighter I got to take care of because I got this. A few years goes by and you realize, I did that, that was fun, but it's so far in the rearview mirror. I graduated from the University of Utah in '96, and I cannot believe that I've done this for 22 years. So that's another thing that, maybe a corollary to what I just said, that 20 years goes by if you kind of put your head down, get after it, get involved in professional organizations, get involved in your community. Once you're out of this very interesting environment, if you put your head down, 20 years goes by very fast. So I recognize also that I'm an old guy up here with a gray beard saying that. So every old guy with a gray beard has probably always said that. You've probably heard this many times, like, it just goes by very fast. It does, especially once you kind of get in a career and really get after it and get involved in things. So take that for what it's worth. So today, I am the engineer of record for the new engineering building over there. I imagine many of you guys saw it go up. We saw it in its many different phases. So I thought it would be kind of interesting to talk about that process, how you take donor money and turn it into a building. Just so as a quick background, I've worked on a lot of different campus type projects and some of the bigger projects in Utah. Many of you might be familiar with the Salt Lake City Public Safety Building a few years ago. Downtown was a $125 million project. Did the Holland Centennial Commons building down at Dixie State. If any of you have spent some time down there, it's the new 5-story, at this point, 5 or 6-year-old building that's right off the freeway. You see as you're going through St. George. Did the Digital Learning Center over at UVU. That was about 10 years ago. That was another 5-story moment frame project that it was kind of the last linchpin that took Utah Valley Community College or Utah Valley State College to a university level, was getting that Digital Learning Center done. I do a lot of work at the doTERRA campus. It's in Pleasant Grove. Some of you might be familiar with. I think you mentioned heading over to Pleasant Grove, but that doTERRA campus is pretty big, so I've done a lot of work there. A lot of the stuff that Point of the Mountain, if you might be familiar with the Ancestry building or Exactware. We also worked on the Adobe building that's right there, right off the freeway. You can see a lot of work going on there now because they're kind of doing that third phase. So, feels like a weird brag, like, hey, I did stuff in my career. That's not it. I'm just trying to let you know these are the type of projects that I've worked on. And then I'm actively working on the new Utah State Prison project, that's going out there kind of west of the airport, which I'm also working on, but there's a lot of soil issues, surprise, surprise, when you try to build right on the edge of a lake. So we are dealing with all of those. So let's talk about the design process a little bit. Just by raise of hands, how many people have stood up here in a seminar type and talked about the design process? What do you hear about it? Just someone throw out some things. The design process. Yeah? Long? Yes? Yeah, especially on a big, complicated project where there's a lot of stakeholders, it can be very, very long. Yeah, here.
It just takes a lot of time.
Yes.
A lot of moving parts that you have to coordinate with. It's not just like one guy.
Yeah, absolutely. There are, again, there are so many stakeholders. There's the people that donated money if it's a project like this one. There are the state, if they're paying money, if it's just a developer who's saying, hey, I'm taking all of this land that I have and I'm cashing it in and building a building, they want to get the best value. And then there's also all the other team members. There's the mechanical and electrical engineers and of course the architect and all of those people. Yeah. What?
Let's go along with that optimization of optimizing the design. Choose the best materials to go.
Right. Yeah, that's awesome, and we're probably going to hit on a couple of those as well. And a word that I wanted to just talk about kind of encompasses some of those things, and it's a part of it, but it's collaborative. It is very collaborative. One of the things that I ask when I interview people that are looking for a job, I ask them several questions, but one of the questions I ask is, what is your learning style? How do you like to learn? Knowing full well that there's not a right answer to that. It's just, the most important thing is you recognize it for yourself. And then the next step of that is, what is your work style? Because again, there's probably not a right or wrong. You just need to recognize it for yourself. If you are one of those people that really can just go in an office or a desk for 6 hours and just put their head down and get stuff done, fantastic. If you're one of those people that really thrives in being in a partnership or in 4 or 5 people and having tasks and you check in every couple hours, great. As long as you know what that is, you can be successful in doing one of these big, long projects with a lot of different stakeholders. If you understand what your learning style and what your work style is, and I also recognize that I'm probably speaking to mostly juniors and seniors with some experience, I'm guessing, at school. But anyways, the point is, to get to this level, you had to at least recognize that for yourself. Like, hey, I learn really well if I do these things. So, what is your learning style and what is your work style? So what I thought I'd do is just share a few of the drawings that I produced for the new engineering building and talk about some of the principles that went into it. I'll quickly describe it, but we can talk about some of the nitty-gritty, but I thought some pictures and some details and how I tried to solve some of those problems, how that happened. So, you might know it's a 5-story building, 2 stories of concrete below, 3 stories of steel above. It is a moment frame, steel moment frame, 3 stories of steel moment frame, 2 stories of concrete moment frame, and we'll talk about how that all came together here in a minute. But one of the things I like to do in my drawings when we're producing things is we use Revit. Everyone's familiar with Revit? It's like 3D version of AutoCAD. So we have to build this model from a production side anyway. So we build this model. So I figure if I put some time into building this model, I would like to at least show it in my drawings. If there's one question or something that the contractor can gain from looking at that and recognizing, oh, this is how this was supposed to go together, I want to show that in the drawings. I've already done the work. I've already paid someone to put all those drawings together, so I want to at least show those in the drawings. There's 3 basic types of software that we use. We use the analysis software, which everyone kind of familiar with. It starts with some Excel or MathCAD, things like that. We use a lot of analysis software. We use the Bentley suite of RAM structural system for our steel, for our concrete. Some people use ETABS. there's different finite element modeling. So there's the analysis side of software that can be a lot of fun, especially when you're right out of school. That is a lot of fun when you can realize, hey, I can spend an hour, I can model 4 or 5 floors really quickly, and I know what every beam size is when you've gone through a class and thought, man, it is like a 2-hour test just to make sure I figured out all my failure mechanisms on this steel beam. It's pretty cool when you realize, hey, this software is pretty powerful. So there's the software side, then there is the production side. There is either Revit, AutoCAD, MicroStation, different software that people use to create the drawings. And then the third bit of software that we use a lot of is just the viewing software. This is the Adobe, right? Yeah, but we also use Bluebeam. There's a couple others, but there's also that just viewing side of it. All 3 of those, it's weird because like being here in school, you think this analysis stuff is where it's at. This is everything that's so important, but in actuality, all 3 of those types of software are just as important. Getting all of that great engineering on the paper so that someone can see it, build it, first bid it, and then build it is super important, and then also just being able to transfer that information back and forth from the viewing side. So, and I'm not as familiar with Adobe, I use Bluebeam a lot more, but again, you can just kind of see the different views of that building. This is a, yeah. This is a view of the kind of the utility tunnels as it's coming out of the building and heading under, heading over to the annex building. And a couple others, just for fun. I thought we'd show those. And then some of the final things, working through the grade of that building. If you guys remember when it was just a big open field, well, some of you might remember. It took so long to build. It had to make up a lot of grade, so one of the ways that we did that is some of these tiered retaining walls, and so I had several sections to try to show, you know, when you're doing an 8-foot tall retaining wall, you can kind of almost pull that one out of the book, and if you get a level slope or a 2-to-1 slope or something, that's going to be pretty standard. You kind of know what it is. But when you're trying to get, you know, 20, 30 feet of making up difference, that's some highway grade stuff, and so we had to kind of show the contractor how to make sure that that all happened. This is a general note sheet. Some of you might be familiar with it. The most important part of this sheet, well, I guess it's all technically important, but the basis of design, this is where we convey information that relates to what is the lateral system of this building, what sort of snow loads did we use, what was our analysis method. This was a dynamic analysis on the building, I think just an equivalent lateral force on the annex building. It's essentially just a 2-story masonry building. But you can kind of see here are, oh yeah, over on that side right there, that basis of design also includes the seismic data. It's information that even going through a plan review comment, the plan checker would want to know, did they design this right? Is it using the right seismic forces? Is it using the right wind forces? It's kind of important. It sort of sets the stage for a lot of the things that are going to happen. I'm boring myself. Am I boring anyone else? I am so sorry. If this is super boring, I apologize. We'll just all get through it, and then if half of you want to leave to go to that lunch at 11:30, that's great. That'll be awesome. We can do that. Sorry about that. All right, so one of the other pages that I think is very important to include in a set of drawings is, like, once you start designing something, what's some of the first things you need to ask yourself? What's one of the first few things you're going to ask yourself? Once you've decided, it's going to be concrete, it's going to be steel, wood, what are some of the things you're going to ask yourself?
Budget.
What's that?
Budget.
Budget? Yeah. Yeah. Once you're starting to design it, like, how much is this going to cost to? Could we design these all with steel, or does it have to be wood? Where does this going to fit? Yeah. Dimensions. Yeah. We need to make sure we have a good understanding of, how long things are going to be, how tall is it going to be, what we're going to put it on. Yeah.
Order, which goes in.
Yep. yeah, how it, kind of that sequence of events. One of the things that we try to do as we're thinking about a detail is, how is that contractor going to build it? Is that feasible to fit bolts in here like this or whatever else? And then one other comment.
Yeah, I was just gonna say, like, how you're going to distribute, like, the loading.
Yep, yeah, and that's what this is right here. I like to include a loading plan for most of my projects, especially one where it's many different uses. An office building, a typical office building live load is 50. A lot of times if it's a composite, concrete on metal deck, you can easily go to 80 on a live load, not really affect those beam sizes, but you get a little, it's a little bit better floor. But on a building like the engineering building, there was just a vast different uses. There's some classroom, there's some auditorium space, there's some lab space. So one of those, those two different functions really started to drive the decision that it needed concrete on the lower level, because I think they've got a dyno lab or something like that. There's some cars in there. I think the mechanical department has. There's several other labs. There was a heavy tank that had 2 or 3 feet of water in it, and so we had to decide, where do all these loads go and how do we? So one of the first things that I like to do is set up a load sheet. So you can kind of see here where I'd said, okay, down here at this, our concrete joist and beam system, we've got that dead load. We've got what our short-term live loads, our long-term live loads, a mass dead load. That's what we're going to include in our seismic. So that's one of the most important. Now, a lot of times this can be a living, breathing document because I want to get this up front because I got to start sizing members, but things might change. Someone might say, hey, guess what? We're going to put a really heavy unit down. One of the things that happened after this thing was all the way built, let's see if I can find the right. They started loading up the floor. I might not be able to find it, but they started loading up the floor, and they. Once it was built, they started loading up the floor, and they said, they're putting like 60,000 pounds of just equipment in this room. Is that okay? And so, taken by itself, that's sure a lot. I mean, that's a lot of load. But just a quick load over area calculation showed that's only like 42 pounds a square foot. It's spread out over an area. I had designed it for 125. I felt very comfortable. Although when the contractor and maybe even some of you guys were like wheeling these pieces of equipment in, like, this is 5,000 pounds. We're putting it right here. Is that okay? And I was like, yeah, I've kind of designed for it. So it was nice to know that I had done the work up front to clearly establish all the loads, so that 2.5 years later, when someone said, we're putting this water jet cutting machine that has 2 feet of water in it, is this going to be okay? Yes, it is. One of the things you guys probably know this, but one of the things I try to help people understand when they talk about how a live load, water is, what's the unit weight of water? 62, 60 something or other, right? So you guys are so close to having just done some physics problems, I'm guessing. In the IBC, it tells you, here's the live loads you can use. If it's 50, if it's 80, a light storage is 125. A lot of times an owner will say, well, yeah, let's just go to that. And I try to explain, 125 is essentially 2 feet of standing water over your entire floor. If that's what you want to do, then that's fine. We can certainly design for it, but understand there's a cost to just say, oh, I want 125 live load. 2 feet of water is that's a lot of water. So, so again, I just assign all of the loads for all the different floors, so I can quickly refer back to it, both at our lab spaces and kind of office space, and up the roof, where we've got snow loads and all the mechanical equipment, things like that. And, oh yeah, this was, put it out of order. This was a similar thing. When the contractor was putting this equipment in, they said, how do you, this is going to be a whole lot, and So I added up all of that load that they told me, and it's like, oh man, that is nearly 100,000 pounds in this room. But then, spread out over an appropriate area, it really only turned out to be about 24 pounds a square foot. Now, maybe in a localized area, if something was truly going to be like 10,000 pounds, yeah, I'd like to know, but spread out over a big area like that, that's certainly doable. And then I did the same thing for the annex building over there, the masonry building. It had some catwalks and some just different loading. I think there's a big blast coal reactor tank in there that we had to design some of the walls for. So, kind of that same idea. Well, time is flying, I apologize. One of the things that we had to do up front is try to understand how we're going to resist the lateral loads in this building, right? Lateral loads get in through wind, more than likely seismic, depending on where you're at, how heavy the building is, all of those things. So, with it being a concrete on the bottom couple levels, the first thought was that I had was concrete shear walls. How do we resist a pretty heavy building and get this to stand up seismically? And so I laid out some concrete shear walls, and this is that collaborative back and forth long process. I said, here is the right lateral system. Now does this work with the layout? And it's not an arbitrary layout that an architect is working with. They're trying to juggle all of the programming for the classroom spaces in the labs and all those things. And trying to stack those two don't usually work very well because classroom's big and open, so where walls worked up above didn't work down below and vice versa. So, all right, if shear walls aren't going to work, then what? We looked at another pretty stiff system, would be some sort of brace frames. Again, just brace frames all the way down, or a version of brace frames up top in the steel, and then shear walls, again, didn't work because these things have to stack and need them to go all the way down. So then we looked at a version of bolt frames on top of concrete shear walls. The same type of a problem. We've got to now deal with different stiffnesses. It's not an impossibility, but you do have to resolve it. So what we finally settled on is 2-story concrete moment frame and a 3-story steel moment frame. And in yellow, I kind of highlighted their locations. You can kind of see what the intent is. Typically, trying to get, the best thing is to get your lateral systems around the perimeter of the building for many reasons, but just intuitively it sounds like that makes sense, right? You want your stiff elements around the outside of the building. Kind of in the north-south direction on this page. North is up. In the north-south directions, I couldn't get enough on each end to really make it work, so we had some interior moment frames. So now how do you think about just like this idea of like, all right, we've got a 5-story moment frame, but halfway up it, I'm going to switch materials. What would you do? I didn't know. I was like, I got to figure this out. I've not done that before. Let's see what we can do. So, what we came up with, that concrete moment frame, that's going to have a lot of rebar in it, right? I mean, there's a lot of rebar in there, and there's going to be a lot of welding in the moment frame. So what we came up with was a cast-in-place. You can kind of see, I'll show you these pictures, but you can kind of see there was this cast-in-place embed plate with some 11 feet long, I think. Some number 11s that were 14 feet long. Weldable rebar right on the bottom with some holes in it to allow concrete to get down. And that is a lot of rebar. So yeah, so this was a lot of, and that, it's weird when you look at a detail. When I look at a detail, I think, yeah, that all makes sense. This is what it's supposed to be. But this is like the 8th or 9th iteration of what that detail is supposed to be. So it's, again, part of that long process of collaborative, like, hey, does this work? Hey, contractor, is this something you want to build? When the contractor was building these cages, you can kind of see the concrete moment frame cage, and then you can kind of see the inlet plate. I really worked on laying these out to make sure that the rebar and all of the dowels would miss, but what we draw is obviously not exactly what they're going to build. We hope they get it close, but it's not exactly there. So they had to crane these in. I think they were like 1,500 pounds or something like that with all that steel. They had to crane them in. And he said, he called me up and he said, I just don't think this is going to fit. I don't know how we're going to get that all in there. And I said, well, if you've got it in a crane, just lift it higher and drop it, see if it spears itself in, and then it'll be good, right? Maybe not. I don't know, maybe contractors don't have... Well, first off, that sense of humor is specifically an engineer, that's not real world funny, that's just sort of like engineer funny. So that you guys gave that a slight chuckle was very gratifying. Thank you. But don't ever think that if you try to say that to someone else that it will get anywhere. Just know engineer humor stays in its own little bubble, and they never cross it. So anyway, so these are just some of the pictures of what, my really nice, simple 8th iteration of that detail looked like and what it took to get that thing built. And, there's some of those huge embed plates stocked up. Other topic. Since this was going up so close to the Clyde, and they were, with the way that the grade was working, we had to figure out a way to resist the soil load that was coming in, right? When it was a concrete shear wall building, those things are stiff enough. We can make them slightly thicker, get enough horizontal rebar in there, and get enough footing to resist the seismic contribution of that soil into there. As soon as we made the decision collectively to go into a MoMA frame, that thing's not stiff enough to take a whole bunch of soil load seismically going into the building. So we had to separate, we tried to decouple all of that seismic mass of the soil and get it out of going into the building. So the contractor put in these temporary walls so they obviously could get down and build. I worked back and forth, again, using the collaborative work with the soils engineer to try to understand how far we had to lay this back. This is some geofoam. How far we had to lay it back so that it could pull enough of the seismic load off of that wall and not let it get into the building. So again, this is sort of the detail, and this is as it. I think I changed it halfway through when they said to truly get this, we're going to be really close to the Wilkins? No. What is the building right now? Clyde, thank you. I'm so sorry. I'm not familiar. But we get so close to the Clyde building. So I changed it up a little bit. I think I changed some of the rebar on the wall. But this was the solution. Give them the detail on how to use some geofoam. That's essentially just really thick, dense plastic that has a pretty good compressive strength or, up against the wall. So this is what it looked like when it was all said and done. You can kind of still see the temporary piles they had to drive for the temporary shoring. Okay. There's another couple pictures of what was going on up at the roof. I never really asked the mechanical engineer this, but I don't understand why the mechanical units are so distasteful to look at. We always have to screen those. I don't know what the deal is. And maybe they know. I've heard many mechanical engineers kind of joke, well, tell us the color you want us to paint it and we'll just paint it because, but every architect wants to make sure that all of their mechanical units are screened, and I don't know if it's fooling anyone. Everyone should know there's something on the roof, but anyways. So usually there is some of this back and forth trying to understand, all right, we've got a mechanical unit and we're going to, all of the building heat and loads and stuff, and they run it through their mechanical engineering magic and say, we need a train or some unit that's this big, that's going to move this much air to heat, and it's going to take up this much space. Well, wouldn't you know it, that space that it takes up very rarely falls along grid lines, and it never is a nice, easy, like, hey, you can just run the building columns all the way up, cantilever them up, create this system to screen it. So a lot of times you have to come up with ways to brace that tall screen wall, because I think this one was 14, 15 feet tall, and it's just sitting on top of the roof. There's a lot of wind on that. We've got to make sure that it doesn't move all around. So I wish this detail was a little more impressive, but it seems kind of small because this is what it turned into. But we usually have to come up with ways to track all those loads down, make sure they get into the building, make sure they get into that roof diaphragm, make sure they get out to all the lateral elements. So again, I think a lot of this stuff inside was exposed, so they galvanized this. I don't often see, it's a good practice, it's a little more expensive, but this was a lot of galvanized steel for that screen wall. You can kind of see. It's, with the mountain in the background, I just talked about humor, now I'm going to talk about engineering art. This picture right here is one of my favorite pictures, just with with the still up and the mountain in the background. I don't know, but again, that's, please don't take my word on what that's a good picture or not, because clearly I don't know. All right, so this is the annex building. Has anyone been in that annex building? It's an interesting building, right? It's super industrial. This is the catwalk right here, and this is kind of a picture of it. Interesting story. I don't know the whole history of why the square footage was established and what it is. It probably was part of the design process at some point, but it was before my time. And I think they said, this is your square footage thing. The administration said, this is the square footage you get for this project. Okay, great. And so that was the number that the architect was working diligently to hit. Like, we have this, we need to fit all this program space in this much square footage. Well, they needed this catwalk because right here, this little round thing, that's that, I think there's a reactor here, and I know there's another one in here, but they needed this catwalk. So the best way to do it was to tie it to that masonry wall in the back, and that's how I had done it. Kind of see it. That's how I had originally detailed it. So it goes in for approval, and they say, oh, this is all floor space. This now counts against your other. So if you want this the way it is, you need to take out space in other parts of the engineering building, and so that wasn't acceptable. So what we did is none of this catwalk ties directly to the wall. It kind of ties through beams, but the grading had to stop so that it could be truly considered a catwalk and not a floor. It seemed like we created some more difficult to build, thus more expensive detailing to satisfy this square footage requirement. Again, I don't understand the rigidity of the square footage requirement, but we created something that was a little more expensive to satisfy that. Kind of the same thing with the building, because we had the moment frame that kind of jogged, and so it had to go all the way down to the foundation, but I didn't want it engaging any of that, because I designed this as kind of a two-story thing. I didn't want it engaging any of the diaphragm, and so it had to be separated. So to do that, the architect said, well, we'll just put it in this kind of room that came down. So there's about a 1,500 square foot room that only houses this column, and no one can access. It's free space, but it can't be considered, I would imagine sometime in the future someone will poke a hole in there and store some neat stuff in there. But right now it's just an empty room that essentially just houses this column, because otherwise it would have exceeded the square footage allotment. So, and it's an interesting thing. I mean, that's not, I don't know, that's not unique for any project. I mean, there's times when you might not even understand, you certainly have to know all the loads and all those parameters, but there's times when you're not going to understand, like, oh no, this donor really wants to use steel, so it can't be, that's your building up. This really has to have some steel in it. It can't all be concrete. Okay, so some of those times, someone mentioned, like, decide the material. It's like, okay, we're sort of going to use steel on that. So there's sometimes those decisions are well beyond what an engineering decision is. It's like, okay, the county only bonded this much. It has to be this type of a project. Yeah.
I'm just wondering why donors dictate the materials that you use.
I don't know. That's a good question. I don't know. That's a good question. I think that was King Hussein, and they had did a lot of steel, and I think he donated a lot. So, which is great because that's how it got built, right? I mean, if, you know, otherwise. But I don't mean to be flippant. I don't understand how they do have a lot of control on, you know, especially on a project like this where it is a lot of donor money. They can control that. So, oh boy, it's 11:14. I'm going to show a couple other quick pictures. That's all below grade stuff. This is kind of, there's the engineering building, there's the annex. This tunnel went through several revisions. A quick story on it. Right around here, it has 7-8 feet of dirt on it. And, you know, I've designed that lid to take that dirt, traffic load, and all that stuff. And it was supposed to be 7,500 PSI concrete. All right, that seems pretty straightforward. The contractor called me up in kind of a panic and said, I don't know what we did, but we poured that whole tunnel lid at 4,000 PSI concrete. What should we do? Well, I don't know. Try again. That's not, I mean, that's what, you know, what you want to say. Oh, shit. That's what you want to say, but the right response is, oh man, let me take a look at that and we'll see what we can do. So my solution here was, instead of supporting a bunch of soil and 110, maybe wet, 120 pounds a cubic foot, I went back to my old friend Geofoam and I said, okay, Geofoam, it probably has a unit weight in, let's say, 2 or 3, 4 pounds a cubic foot. Let's replace 5 of those feet of dirt with Geofoam, and then we'll put the dirt on top of it, and no one will be wiser until I spill it to all my closest friends in this. And you know, it'll affect, oh yeah, this was how I explained it to him. You know, I don't know, maybe in 10 years it'll get closer to that 7,500. It just was never going to get 7,500 in a 28-day break or a 56-day break. So anyway, so this is where I had to explain to him, like, yeah, you need to put 5 feet of geofoam right on top of that tunnel lid, and then we should be okay. I will show just a couple of the pictures and tell a couple of quick more stories. Yeah, so the concrete part is a pan joist. It's not just a flat system. It's a, you know, we had to integrate the concrete mold frame. We had to integrate the pan joists with all the mold frame beams, and that was a challenge. Not in like, oh, it's insurmountable, but that's just a different style of construction, especially for what is typically done here in Utah. And then you can see a lot of the different areas, framing, the way I do things in my drawings. It's a roof framing plan. I wrote a couple details that I thought at one point might. Oh, I was gonna. Okay. This is the southeast corner, and the next time you guys walk by it, notice this corner right here. We're going to zoom in a little bit. Apologize, I'm not very good at zooming this around. Okay, so let's see if this works. We can do different pages. All right, well, either way, this was the stair, but for some reason the architect really liked this idea that this stair in this corner is just sort of going to cantilever out, just sort of float out there, so that all of those columns that make up a really good stair, you know, because they're going to pick up the landing beam and all that stuff, they just didn't want them to go down. So it's a neat feature. I don't know if it necessarily adds a whole lot, but that sounds like I'm going to go. So that I'm not. I mean, it is a pretty neat feature, but it's just it felt like a weird thing to spend some money on just not having 7.5 feet of columns go down. But anyway, so I had to come up with a bunch of different details because now we had to take a cantilevered steel stair element and try to tie it back into a concrete mold frame building and also a steel mold frame building. So a lot of those details turned into a bunch of embed plates and welding, as you would expect. And anyways, that's just kind of what it looked like. I came up with this idea to put a haunch, an in-bed plate with a haunch in that concrete mold frame beam, and then allow it to cantilever out, and then try to account for the different, the forces resulting from the different story drift that are going to be there. Try to take care of all that. So it's 11:47. If you normally end around 11:50. All right. So any other questions? I sometimes talk fast. I really do enjoy engineering. There's a lot of really great things that happen in the world of engineering, both structure and otherwise. Yeah.
I was curious, you mentioned at the beginning using your 3D models with contractors and things. Are they usually pretty familiar with Revit and that software, or do you have to
They're pretty sophisticated now. This contractor was Jacobson, but the big guys here in Salt Lake, Biggie or Lady Oakland, Jacobson, all of them, they all use it. They also use some software called Navisworks, which is, it reads 3D files and creates sort of like the Revit file has a whole bunch of different properties associated with all the different objects, and that file can get huge. If all of those properties are stripped away, they can use Navisworks and then do like clash detection with all the piping, with all the ceilings and all those things. So, but yeah, they are pretty savvy as it comes to using 3D modeling software. Okay, oh yeah, a couple, right here.
So you talked a lot about like working with like architects and having to change things because of what they were doing. Like, do you have to collaborate a lot with like the ones that the guys that are designing the pipe people, you have to like deal with all that as well?
Yeah, there's sometimes a lot of mechanical engineers, they're gonna need to run a duct, and I want them to run a duct because I don't want it to be too hot or cold, so they should run a duct. And so we'll figure out a good way to either run between beams or go through a steel beam. Sometimes an electrical engineer might say, hey, I need this room, and I'm going to need a 6x6 area where I just have to run all this conduit. Can we box it out? So yeah, we'll go back and forth like that. It's a pretty open back and forth because part of it is I don't want to stonewall them. I mean, I want this building to function and everyone to be happy as well. Yeah. Well, you use the term resilience, and that has a bit of a different connotation kind of nowadays, but as far as the lateral loads as it relates to what is this going to see seismically, it's through those moment frames, through the concrete moment frames and the steel moment frames. It's a special steel concrete moment frame system. They have two different response spectra, so we had to make those work, but yeah, it was through the moment frames. All right, well, thank you, everyone. I'll stick around and answer any, if there's a question or two. I do enjoy talking about engineering. I do enjoy talking about that building, but I also enjoy talking about other things, just not in this kind of setting. But yeah, so I'll stick around if you guys have any questions, but thank you for your time.